Introduction to Java Programming. Java is a high-level, class-based, object-oriented programming language that is designed to have as few implementation dependencies as possible. It is a general-purpose programming language intended to let application developers write once, run anywhere, WARA, meaning that compiled Java code can run on all platforms that support Java without the need for recompilation. Java applications are typically compiled to bytecode that can run on any Java virtual machine, JVM, regardless of the underlying computer architecture. This portability is one of Java's most significant advantages, making it widely used across various domains. Its robust nature and strong community support contribute to its enduring popularity in software development. The Java platform consists of several components crucial for development and execution. The Java Development Kit, JDK, is a software development environment used for developing Java applications and applets. It includes the Java Runtime Environment, JRE, and a set of development tools. The JRE provides the libraries and JVM needed to run Java programs. The JVM is an abstract machine that enables a computer to run Java programs, translating Java bytecode into machine-specific instructions. Understanding these components is fundamental to beginning your journey in Java programming. Setting up your Java environment. Before you can begin writing Java programs, you need to set up your development environment. The first crucial step involves installing the Java Development Kit, JDK, which includes the Java Runtime Environment, JRE, and the necessary compilers and debuggers. You can download the latest version of the JDK from Oracle's official website, or choose an open-source alternative like OpenJDK. Ensure you select the correct version compatible with your operating system, whether it's Windows, Mac OS, or Linux. Following the installation instructions carefully will prevent common setup issues and ensure all components are correctly placed on your system. After installing the JDK, it is often necessary to configure environment variables, specifically the Java Home variable, and updating the path variable. Java Home typically points to the root directory of your JDK installation, while adding the JDK's bin directory to your system's path allows you to execute Java commands from any directory in your terminal. Finally, choosing an integrated development environment, IDE, like IntelliJ IDEA, Eclipse, or VS Code can significantly enhance your coding experience. These IDEs provide features such as code completion, debugging tools, and project management, streamlining the development process and boosting productivity for Java programmers. Your first Java program. Writing your first Java program is an exciting milestone. Every standalone Java application begins with a main method, which serves as the entry point for program execution. The basic structure involves defining a class, typically named Hello World, and within that class, declaring the public static void main string args method. This method's signature is crucial and must be precise for the Java Virtual Machine, JVM, to locate and execute your code. Inside the main method, you will place the instructions that your program needs to perform. This foundational structure is the blueprint for all subsequent Java applications you will create. To make your first program interactive, you can use systemout.println to display output to the console. This statement prints a line of text or the value of a variable to the standard output stream, followed by a new line character. For example, systemout.println hello world includes the classic greeting. After writing your code in a .java file, you compile it using the javacs command in your terminal, which creates a .class file containing bytecode. Finally, you execute the program using the java command, followed by the class name, allowing you to see your output. This simple process demonstrates the compile and run cycle fundamental to Java development. Java syntax and basic data types. Understanding Java syntax is crucial for writing correct and readable code. Java is a case-sensitive language, meaning my variable and my variable are treated as different entities. Every statement in Java typically ends with a semicolon, and code blocks are defined using curly braces. Comments, denoted by // for single line or // for multi-line, are essential for explaining your code and are ignored by the compiler. Identifiers are names given to classes, methods, variables, and packages, and they must follow specific rules, such as starting with a letter, underscore, or $sign. Java also has a set of reserved keywords that cannot be used as identifiers, like public, static, and void. Java provides several primitive data types to store different kinds of values. These include byte, short, int, and long for whole numbers, with varying ranges of storage. For floating point numbers, float and double are available, with double offering higher precision. The Boolean type stores true or false values, essential for logical operations. Finally, the char type is used to store a single character. Variables are named memory locations that hold data, declared with a specific data type, while constants are variables whose values cannot be changed after initialization, often denoted by the final keyword. Choosing the appropriate data type is important for efficient memory usage and accurate computations. Operators in Java. Operators are special symbols that perform operations on one or more operands. Java supports a rich set of operators categorized into several types. Arithmetic operators such as plus, minus, star, divide, and percent, modulo, perform mathematical calculations. Relational operators, including equals equals, not equals, time, greater than, equals percent, and equals are used to compare two values, resulting in a Boolean, true or false. Logical operators, and. Combine or negate Boolean expressions, crucial for complex conditional logic. Assignment operators, like equals, plus equals, minus equals, simplify assigning values to variables. Understanding these operators is fundamental for constructing expressions and controlling program flow. Beyond the basic types, Java also includes increment, and decrement operators, which are unary operators used to increase or decrease the value of a variable by 1. These are commonly used in loops and counters. Operator precedence dictates the order in which operators are evaluated in an expression, similar to mathematical order of operations. For instance, multiplication and division generally take precedence over addition and subtraction. Parentheses, O double set, can be used to explicitly control the order of evaluation, ensuring that complex expressions are computed as intended. Mastering operator precedence helps prevent logical errors and ensures your code behaves predictably. Control flow, conditional statements. Conditional statements are essential programming constructs that allow your program to make decisions and execute different blocks of code based on whether a specified condition is true or false. The if statement is the most basic form, executing a block of code only if its condition evaluates to true. The if-else statement extends this by providing an alternative block of code to execute when the if condition is false. For scenarios involving multiple conditions, the if-else ladder allows you to test a series of conditions sequentially, executing the first block whose condition is met. These structures are fundamental for creating dynamic and responsive programs. Another powerful conditional statement in Java is the switch statement. It provides a way to execute different code blocks based on the value of a single variable or expression. The switch statement is particularly useful when you have a variable that can take on several distinct values and you want to perform different actions for each value. Each case label within the switch block specifies a possible value, and the break statement is used to exit the switch once a match is found, preventing fall-through to subsequent cases. A default case can be included to handle situations where none of the specified case values match. Properly utilizing switch statements can lead to cleaner and more efficient code compared to a long if-else-if chain for certain scenarios. Control flow looping constructs. Looping constructs are fundamental in programming for executing a block of code repeatedly. The for loop is ideal when you know exactly how many times you want to iterate. It consists of an initialization, a termination condition, and an increment-decrement statement, all defined in a single line. This structure makes for loops very concise and readable for counter-controlled iterations. The while loop, on the other hand, is used when the number of iterations is not known beforehand, and the loop continues as long as a specified condition remains true. It's crucial to ensure that the condition eventually becomes false, to avoid infinite loops, which can crash your program. These loops are cornerstones for automating repetitive tasks and processing collections of data. The do-while loop is similar to the while loop, but with one key difference. Its block of code is executed at least once before the condition is evaluated. This makes it suitable for scenarios where you need to perform an action at least once, regardless of the initial condition, and then continue looping based on subsequent checks. Additionally, break and continue statements offer fine-grained control within loops. A break statement immediately terminates the innermost loop, transferring control to the statement immediately following the loop. The continue statement, conversely, skips the current iteration of the loop and proceeds to the next iteration, allowing you to bypass specific parts of the loop's body under certain conditions. These control statements provide flexibility in managing loop execution. Arrays in Java. Arrays in Java are fundamental data structures used to store multiple values of the same data type in a single variable. They provide a way to organize and manage collections of related data efficiently. When declaring an array, you specify the data type of its elements, followed by square brackets, and then the array name. For example, int asterisk declares an array that can hold integers. Initializing an array involves allocating memory for its elements, typically using the new keyword and specifying the array's size, such as numbers equals new int 5. Alternatively, you can declare and initialize an array simultaneously by providing a list of values enclosed in curly braces, like string.names equals Alice, Bob, Charlie. Understanding array declaration and initialization is crucial for handling structured data in Java. Once an array is declared and initialized, you can access individual elements using their index, which is a zero-based integer. So the first element is at index 0, the second at 1, and so on, up to array.length -1. For example, number 0 would access the first element of the numbers array. You can also modify elements by assigning new values to a specific index. Java also supports multi-dimensional arrays, which are essentially arrays of arrays. A common example is a two-dimensional array, often used to represent matrices or tables, declared as int matrix equals new int 3, 3. Iterating through arrays, especially multi-dimensional ones, typically involves using loops to process each element. Efficiently manipulating array elements is a core skill for any Java programmer. Introduction to Object-Oriented Programming, OOP. Object-Oriented Programming, OOP, is a programming paradigm that uses objects, data structures consisting of data fields and methods, to design applications and computer programs. This approach contrasts with traditional procedural programming, which focuses on sequences of instructions. OOP aims to model real-world entities as software objects, making code more modular, reusable, and easier to maintain. The core concepts of OOP are encapsulation, inheritance, polymorphism, and abstraction, often referred to as the 4 pillars of OOP. Embracing OOP principles leads to more organized and scalable software architectures, which is a significant advantage in complex projects. The primary motivation behind adopting OOP is to manage complexity in large software systems. By breaking down a problem into smaller, self-contained objects, developers can focus on individual components without being overwhelmed by the entire system. OOP promotes code reusability through inheritance, allowing new classes to inherit properties and behaviors from existing ones, reducing redundancy. It also enhances maintainability, as changes to one object are less likely to affect others thanks to encapsulation. Furthermore, polymorphism enables objects of different classes to be treated as objects of a common type, leading to more flexible and extensible code. These benefits collectively make OOP a dominant paradigm in modern software development, especially in languages like Java. Classes and objects. In Java, a class serves as a blueprint or a template for creating objects. It defines the common properties, attributes or fields, and behaviors, methods that all objects of that class will possess. For example, a car class might define attributes like color and make, and methods like start and stop. Defining a class involves specifying its name, followed by curly braces containing its members. Classes encapsulate data and the methods that operate on that data, forming the fundamental building blocks of object-oriented programming. This structured approach helps in organizing code and modeling real-world entities effectively. An object is an instance of a class. When you create an object, you are essentially creating a concrete realization of the blueprint defined by the class. For instance, if car is a class, then my car equals new car creates an actual car object. Objects have their own unique state, values of their attributes, and can perform actions defined by their class's methods. Creating objects, also known as instantiation, involves using the new keyword followed by the class constructor. Through objects, you can interact with the data and functionality defined in the class, allowing your program to manipulate real-world concepts in a structured and organized manner. Understanding the relationship between classes and objects is paramount to grasping OOP in Java. Constructors. Constructors are special methods in Java used to initialize objects. When you create a new object using the new keyword, a constructor is automatically called. The primary purpose of a constructor is to set the initial state of the object, assigning values to its instance variables. A constructor has the same name as its class and does not have a return type, not even void. If you do not explicitly define any constructor in your class, Java provides a default constructor that takes no arguments and initializes instance variables to their default values, e.g., 0 for numbers, null for objects, false for booleans. Understanding constructors is crucial for ensuring objects are properly set up upon creation. Java allows you to define multiple constructors within a single class, a concept known as constructor overloading. This enables you to create objects in different ways, providing flexibility based on the initial data available. For example, a person class might have one constructor that takes a name and age, and another that only takes a name with age defaulting to a specific value. Inside a constructor, you can use the this keyword to refer to the current object's instance variables, distinguishing them from local parameters with the same name. You can also use this to call another constructor within the same class, which is useful for avoiding code duplication when multiple constructors share common initialization logic. Effective use of constructors ensures robust object initialization and promotes cleaner code. Methods in Java. Methods in Java define the behaviors or actions that an object can perform. They are blocks of code that are executed when called, allowing you to encapsulate specific functionalities. Every method has a return type, which specifies the type of value the method will send back after its execution, or void if it doesn't return any value. Methods can also accept parameters, which are input values passed into the method to influence its behavior. Defining a method involves specifying its access modifier, e.g. public, return type, name, and a list of parameters in parentheses. This structure allows for modular and reusable code, making programs easier to understand and maintain. Method overloading is a powerful feature in Java that allows a class to have multiple methods with the same name but different parameter lists. The parameter lists must differ in the number of parameters, their data types, or the order of their data types. The return type alone is not sufficient to differentiate overloaded methods. This enables you to provide different implementations of a method that perform similar tasks but operate on different types or quantities of input. For example, a calculator class might have multiple add methods, one for 2 integers, another for 3 integers, and one for 2 doubles. When an overloaded method is called, the Java compiler determines which specific method to invoke based on the arguments provided during the call, a process known as static polymorphism. This flexibility enhances code readability and reduces the need for distinct method names for similar operations. Encapsulation and access modifiers. Encapsulation is one of the fundamental principles of object-oriented programming, OOP, in Java. It refers to the bundling of data, attributes, and the methods that operate on that data within a single unit, typically a class. More importantly, encapsulation involves restricting direct access to some of an object's components, preventing external code from directly manipulating internal data. This protection is achieved through access modifiers, which control the visibility of classes, fields, and methods. By hiding the internal implementation details, encapsulation promotes data integrity and allows for changes to the internal structure of a class without affecting external code that uses it. This principle is crucial for building robust and maintainable software systems. Java provides 4 access modifiers: public, private, protected, and default, no keyword. The public modifier grants access from anywhere, making elements universally visible. Private restricts access to only within the declaring class, effectively hiding implementation details and enforcing encapsulation. Protected allows access within the same package and by subclasses in any package. The default modifier, also known as package private, allows access only within the same package. To interact with private data, classes typically provide public getter, accessor, and setter mutator methods. These methods offer controlled access to the internal state, allowing validation or transformation of data before it is set or retrieved. Proper use of access modifiers and getter-setter methods is key to implementing effective encapsulation in Java. Inheritance. Inheritance is a core OOP principle that allows a class to acquire the properties and behaviors of another class. This mechanism promotes code reusability and establishes an is-a relationship between classes. The class that is inherited from is called the parent class, superclass, or base class, while the class that inherits is called the child class, subclass, or derived class. In Java, the extends keyword is used to indicate that a class is inheriting from another. For example, class dog extends animal, that means dog inherits from animal. This hierarchical relationship allows subclasses to reuse existing code from their superclass and add their own unique functionalities. Inheritance is a powerful tool for creating a structured and organized class hierarchy. When a subclass inherits from a superclass, it gains access to the superclass's non-private fields and methods. The super keyword is used to refer to the immediate parent class object. It can be used to call a superclass's constructor from a subclass constructor, or to access a superclass's method or field that has been overridden or shadowed in the subclass. Method overriding is a key aspect of inheritance, where a subclass provides a specific implementation for a method that is already defined in its superclass. The method signature, name, parameters must be the same. This allows for specialized behavior in subclasses while maintaining a common interface defined by the superclass. Understanding inheritance is vital for designing flexible and extensible Java applications. Polymorphism, meaning many forms, is a core OOP concept that allows objects of different classes to be treated as objects of a common type. In Java, polymorphism is primarily achieved through method overriding, runtime polymorphism, and method overloading, static polymorphism. Runtime polymorphism, also known as dynamic method dispatch, occurs when a superclass reference variable holds an object of a subclass. A specific method implementation that is called is determined at runtime based on the actual type of the object, not the type of the reference variable. This enables a single interface to represent different underlying forms, making code more flexible and adaptable. It is a powerful feature for designing extensible and maintainable software. Static polymorphism, or compile-time polymorphism, is achieved through method overloading, where multiple methods in the same class have the same name but different parameter lists. The compiler determines which overloaded method to invoke based on the number and types of arguments passed during the method call. This resolution happens at compile time. Another aspect of polymorphism involves upcasting and downcasting. Upcasting occurs implicitly when a subclass object is assigned to a superclass reference, always safe. Downcasting, converting a superclass reference to a subclass type, requires an explicit cast and can lead to a class cast exception if the object is not actually an instance of the target subclass. Polymorphism is crucial for writing generic, flexible code that can work with various object types through a common interface. Abstraction. Abstract classes and interfaces. Abstraction is an OOP principle that focuses on showing only essential information and hiding the complex implementation details. In Java, abstraction is achieved primarily through abstract classes and interfaces. An abstract class is a class that cannot be instantiated directly and may contain abstract methods declared without an implementation. It is declared using the abstract keyword. Abstract classes serve as blueprints for other classes, forcing subclasses to provide implementations for the abstract methods. This ensures that all subclasses adhere to a common structure and behavior while allowing for variations in their specific implementations. Abstract classes can also contain concrete, non-abstract methods and fields, providing a mix of defined and undefined behaviors. Interfaces in Java provide a complete abstraction, defining a contract for behavior without any implementation details. An interface contains only abstract methods, implicitly public and abstract, and public static final fields, constants. Classes implement an interface using the implements keyword, and they must provide an implementation for all the methods declared in the interface. Unlike abstract classes, a class can implement multiple interfaces, allowing it to inherit behaviors from several sources, addressing the limitation of single inheritance in Java. Interfaces are crucial for achieving loose coupling and designing highly flexible and extensible systems. The choice between an abstract class and an interface depends on the specific design requirements, with abstract classes being suitable for is-a relationships with some common implementation, and interfaces for can-do capabilities. Packages in Java. Packages in Java are a mechanism for organizing classes, interfaces, and subpackages into logical groups. They provide a way to modularize code, prevent naming conflicts, and control access to classes. Think of packages as folders in a file system, where related files are grouped together. The package statement, which must be the first non-comment statement in a Java source file, declares the package to which the class belongs. For example, package com example myapp indicates that the class is part of the myapp package within the com example hierarchy. This hierarchical naming convention helps in creating unique package names, preventing clashes between classes with the same name developed by different organizations. Proper package organization is crucial for managing large and complex Java projects. To use classes from other packages, you typically employ the import statement. The import statement allows you to refer to classes by their simple names rather than their fully qualified names, which include the package path. For instance, import java.util ArrayList allows you to use ArrayList instead of java.util ArrayList. You can also import all classes from a package using a wildcard, like import java.util*. Though this is generally discouraged in production code for clarity and to avoid potential naming conflicts, Java's standard library is organized into numerous packages, such as java.lang, fundamental classes, implicitly imported, java.util, utility classes, and java.io, input-output operations. Creating your own packages involves defining a directory structure that mirrors the package name, ensuring that the compiler can locate your classes. Effective use of packages contributes significantly to code maintainability and scalability. Exception handling. Exception handling is a critical aspect of robust Java programming, allowing you to manage runtime errors gracefully without crashing your application. An exception is an event that disrupts the normal flow of a program. When an error occurs, Java creates an exception object, which is then thrown. You can catch these exceptions using a try-catch block. The try block contains the code that might throw an exception, and the catch block specifies the type of exception it can handle and the code to execute if that exception occurs. This mechanism separates error-handling code from normal program logic, making your code cleaner and more readable. Properly handling exceptions ensures that your application can recover from unexpected situations and continue execution. The finally block is an optional part of a try-catch statement that always executes, regardless of whether an exception was thrown or caught. It is typically used for cleanup operations, such as closing file streams or database connections, ensuring that resources are properly released. The throw keyword is used to explicitly throw an exception from within your code, often when a method detects an error condition it cannot handle. The throws keyword, on the other hand, is used in a method signature to declare that a method might throw one or more specified types of checked exceptions. Java distinguishes between checked exceptions, which must be declared or caught, and unchecked exceptions, runtime exceptions, which do not need to be explicitly handled. Understanding these concepts is vital for writing resilient and fault-tolerant Java applications. Input-output I/O operations. Input-output I/O operations are fundamental for any program that needs to interact with the outside world, whether it's reading user input from the console, writing data to a file, or communicating over a network. In Java, the java.io package provides a rich set of classes for performing I/O. For basic console input, the scanner class is widely used. It allows you to read various types of user input, such as integers, strings, and doubles, from the standard input stream, system_in. Writing output to the console is typically done using system.out.println or system.out.print, which send data to the standard output stream. These console I/O methods are essential for simple user interaction and debugging purposes. Beyond console interaction, Java provides robust capabilities for file I/O. Reading from a text file often involves using classes like file reader combined with buffered reader for efficient character-by-character or line-by-line reading. Similarly, writing to a text file can be achieved using file writer and buffered writer. These classes allow you to open files, write data to them, and close them properly, which is crucial for preventing data corruption and resource leaks. For binary data, file input stream and file output stream are used. Understanding how to perform file I/O is vital for applications that need to persist data, load configurations, or process large data sets. Always remember to handle potential I/O exceptions when working with I/O operations, as files might not exist or permissions might be insufficient. Collections Framework Overview. The Java Collections Framework is a set of interfaces and classes in the java.util package that provides a unified architecture for representing and manipulating collections of objects. It offers a standardized way to handle groups of data, making it easier to store, retrieve, and process elements. The framework includes interfaces like list, set, and map, which define the fundamental types of collections, along with various concrete implementations for each. This framework significantly simplifies common programming tasks related to data management, such as storing a list of items, managing unique elements, or associating keys with values. Understanding the collections framework is crucial for efficient data handling in Java applications. The primary benefits of using the collections framework include increased programmer productivity, improved program performance, and enhanced software reusability. Instead of writing custom data structures for every need, developers can leverage the optimized and well-tested implementations provided by the framework. The core interfaces define the behavior, while concrete classes like ArrayList, HashSet, and HashMap provide the actual data structures. These implementations offer various performance characteristics, allowing developers to choose the most suitable one for their specific use case. The framework also includes utility classes, like collections, for static methods that operate on collections, and arrays, for array-related utilities, further enhancing its power and flexibility. Mastering the collections framework is a hallmark of an effective Java developer. Working with lists, ArrayList, linked list. The list interface, part of the Java collections framework, represents an ordered collection of elements, also known as a sequence. Lists allow duplicate elements and maintain the insertion order. You can access elements by their integer index, similar to arrays. Two of the most commonly used implementations of the list interface are ArrayList and linked list. ArrayList is a resizable array implementation, meaning it dynamically grows or shrinks as elements are added or removed. It provides fast random access to elements, retrieval by index, but can be slower for insertions or deletions in the middle of the list, as it requires shifting subsequent elements. It is generally preferred when frequent element access is needed. Linked list, on the other hand, implements the list interface using a doubly linked list data structure. Each element in a linked list stores a reference to both the previous and next elements in the sequence. This structure makes linked list very efficient for insertions and deletions at any position, as it only requires updating a few pointers. However, random access to elements is slower compared to ArrayList, because traversing the list from the beginning or end is necessary to reach a specific index. Common list methods include add, get, set, remove, and size. Choosing between ArrayList and linked list depends on the specific use case and the frequency of different operations. For example, if you frequently add or remove elements from the middle of a large list, linked list might be more suitable. whereas ArrayList excels in scenarios requiring frequent element retrieval by index. Working with sets, hash set, tree set. The set interface in the Java Collections framework represents a collection that contains no duplicate elements. It models the mathematical set abstraction. Unlike lists, sets do not maintain any specific order of elements. The order in which elements are stored or retrieved is not guaranteed. The primary purpose of a set is to ensure uniqueness among its elements. If you attempt to add a duplicate element to a set, the operation will typically be ignored and the set will remain unchanged. This characteristic makes sets ideal for scenarios where you need to store a collection of distinct items, such as a list of unique user IDs or keywords. Understanding the uniqueness property is key to effectively using sets. Two common implementations of the set interface are hash set and tree set. Hash set stores its elements in a hash table, offering excellent performance for basic operations like add, remove, and contains, with an average time complexity of 0.1. However, hash set does not guarantee any order of elements. Tree set, on the other hand, stores its elements in a balanced binary search tree, which means elements are stored in a sorted ascending order. This sorted nature comes at the cost of slightly slower performance for basic operations, typically O log n. Tree set is particularly useful when you need to maintain a sorted collection of unique elements or perform range-based queries. Both hash set and tree set provide methods for set operations like union, intersection, and difference through methods like add all, retain all, and remove all. Choosing between them depends on whether you prioritize raw performance and unordered storage, hash set, or sorted storage, tree set. Working with maps, hash map, tree map. The map interface in the Java Collections framework represents a collection of key-value pairs. Each key in a map must be unique, and it maps to exactly one value. Maps are incredibly useful for storing and retrieving data, where each piece of information has a unique identifier. They are not considered true collections in the sense that they do not extend the collection interface, but they are an integral part of the framework for managing associated data. Common use cases include storing configuration settings, user profiles, or any data where quick lookup by a unique key is required. Understanding the key-value pair concept is fundamental to working with maps. Two prominent implementations of the map interface are hashmap and tree map. Hashmap stores its entries in a hash table, providing excellent average case performance, 0.1, for operations like put, get, and remove. However, hashmap does not guarantee any order of its key-value pairs. Tree map, conversely, stores its entries in a balanced binary search tree, which means the entries are sorted according to the natural order of their keys or by a custom comparator. This sorted order comes with a slightly higher time complexity of O log n for basic operations. Tree map is particularly useful when you need to iterate over the map entries in a sorted order or perform range-based queries on keys. Common map methods include put, get, remove, contains key, contains value, key set, and values. The choice between hashmap and tree map depends on whether you prioritize speed and unordered storage, hashmap, or sorted storage and ordered iteration, tree map. Generics in Java. Generics were introduced in Java 5 to provide type safety to collections and to eliminate the need for explicit casting. Before generics, collections stored objects of type object, which meant that elements retrieved from a collection had to be explicitly cast to their original type, leading to potential class cast exceptions at runtime. Generics allow you to specify the type of objects that a collection will hold at the time of its declaration. Such as ArrayList, this type information is then used by the compiler to enforce type checks at compile time, catching potential errors much earlier in the development process. This significantly improves code reliability and readability, as the type of elements in a collection is clear from its declaration. Beyond collections, generics can also be applied to classes and methods, allowing you to create reusable components that work with various types while maintaining type safety. A generic class, like box, can operate on objects of type T, where T is a type parameter specified when the class is instantiated. Similarly, generic methods can accept type parameters, enabling them to work with different data types without being rewritten for each specific type. For example, a generic method, public void printArray array, can print arrays of any type. Type parameters are typically single uppercase letters. The primary benefits of generics include stronger type checks at compile time, elimination of casts, and enabling programmers to implement generic algorithms. Understanding and utilizing generics is crucial for writing modern, type-safe, and robust Java code. Introduction to multithreading. Multithreading is a programming concept that allows a program to execute multiple parts of code concurrently, meaning they can run seemingly at the same time. Each independent path of execution is called a thread. In a single-threaded application, tasks are executed sequentially, one after another. However, in a multi-threaded application, different threads can perform different tasks simultaneously, leading to improved performance and responsiveness, especially in applications that involve long-running operations or user interfaces. For example, a word processor can check spelling in one thread while the user types in another. Understanding multithreading is crucial for developing high-performance and responsive Java applications. In Java, there are two primary ways to create a thread: by extending the thread class or by implementing the runnable interface. When you extend the thread class, you override its run method, which contains the code that the thread will execute. To start the thread, you create an instance of your class and call its start method, which in turn calls the run method in a new execution thread. Alternatively, by implementing the runnable interface, you also provide an implementation for the run method. An instance of this runnable class is then passed to a thread object, and its start method is called. Implementing runnable is generally preferred because Java does not support multiple inheritance of classes, allowing your class to extend another class while still being multi-threaded. Threads typically go through various lifecycle stages: new, runnable, running, blocked, and terminated. Managing these stages and ensuring proper synchronization between threads is key to avoiding common concurrency issues. Advanced Java topics and next steps. Having covered the core concepts of Java programming, you are now well equipped to explore more advanced topics and specialized areas. Modern Java development heavily utilizes features like Lambda expressions, which provide a concise way to represent anonymous functions, making code more readable and functional. The Streams API, often used in conjunction with Lambdas, offers a powerful and declarative way to process collections of data, enabling efficient filtering, mapping, and reduction operations. These features significantly enhance the expressiveness and conciseness of Java code, especially for data manipulation tasks. Further exploration into these areas will deepen your understanding of contemporary Java programming practices. Beyond language features, practical application development often involves interacting with databases using JDBC, Java Database Connectivity, which provides a standard API for connecting to and querying relational databases. For building graphical user interfaces, GUIs, frameworks like JavaFX or Swing are available, allowing you to create desktop applications with rich visual components. Web development with Java involves frameworks like Spring Boot or Jakarta EE, formerly Java EE, which are essential for building enterprise-grade web applications and microservices. To continue your learning journey, consider working on personal projects, contributing to open-source initiatives, or pursuing specialized certifications. The Java ecosystem is vast, offering endless opportunities for growth and specialization in various domains.